Hey guys, this is Michael. Welcome back to the sixth and probably final episode of Let's Try Hardware Engineering. So we're on to sequential logic now, and let's see. So we know that sequential logic, it depends on not only the present value of its signals, but the sequence of past inputs, its input history. So, components used in sequential logic have an internal state stored within them. It can be later used for evaluation. Think of them as functional memories. So, we're going to be working with latches and flip-flops, but they haven't been used in memory for some time now, but they do work. Let's see. Possibly the simplest form of circuit capable of preserving a value is a latch. Latches differ in their structure and truth tables, but the general principle is the same. Almost all of them have a set and reset input that sets set 1 and reset 0, their internal state respectively. Then there's usually a variation of inputs which signifies that the value should be held and not altered. Again, it depends on the type of latch. It's simple. When you want to store 1, configure set to 1 and reset to 0. Exchange the states of set and reset if you want to store 0. And when you want to hold the value, just remember it. No storing, set and reset must be 0. Avoid set 1, reset 1. So we'll keep that up just in case we need to reference it. And this time they want us to develop a gear control for a civil aircraft. Aircraft gear can be up or down. We need to be able to lift the gear if it's down, put it down if it's up, and to prevent gear manipulation when the systems are locked. Put gear down is 1 when putting the gear down the gear is requested before landing. That's this guy right here. Lift gear up is 1 when lifting the gear up is requested after takeoff. That's this guy here. And systems locked is 1 when lifting and putting the gear down should not be allowed. That's systems locked right here. Although not a listed input, internal status must be used for correct results. It is 0 when gear is down and 1 when gear is up. Gear up is 1 when the gear is up. I'm going to grab one of these just in case we need it, and I'm going to grab one of these just in case we need it. And then we got a few new components here. These are used to pull a line up or down, depending, making it logic low or high if we needed that functionality, but I don't believe we do. And here's the new latch we have access to. This is called an SR latch, and actually let's not pull it out of there so we can still get the description. It's odd that when you pull a component under the table, you can't get this verbose description anymore, at least not that I'm aware of. So an SR latch is one of the components considered sequential. Latches in general are capable of storing a value, and their inputs are known for altering the state when a certain event, i.e. a certain input variation occurs. SR latch stores its internal state, making the S set input 1 changes the state. The stored value to 1. R reset changes the internal state to 0. Avoid the SR equals 1 combination. The behavior is not defined. Outputs Q and Q bar give the internal state and its negation respectively. Okay. So I think we're going to need these SR latches to store our data. Well, we only need one data, right? And the output of that, I think it's probably going to be Q, but let's go ahead and connect it up. So this is the Q is the actual data. The Q bar is the knotted data. But now what do we need to do? Actually, let me get rid of that. And we'll just move this up here like that. Just let it connect automatically. I don't think we're going to need that, actually. I don't think we're going to need that. But I do think we're going to need a couple logic gates. Okay. So is there a truth table? Following truth table is going to be something we haven't had here before. It's actually a sequence of inputs, each one depending on the previous. Let's look at it and see. Put gear down, lift gear up. Status of the latch, maybe? I don't know what these mean. It's not giving me an overhead. But anyway, we know what the story is. So when put gear down is a 1, we're going to change the internal data of the latch to, let me see what their values are. I really don't like this changing interface. I never know where to click. Okay. Put gear down is a 1 when putting down the gear is requested before 1. 0, okay, so 0 when the gear is down and 1 when the gear is up. So when put gear down is 1, we put the gear down, and therefore the value of what's in the latch here should go to 0. When put gear up is 1, we should lift the gear, and the internal state should then be 1. So this is what's going to make it into a 1. This is what's going to make it into a 0. And then this guy, if it's a 1, we're not supposed to do anything up here. So how do we do that? Well, what it says about an SR latch is that if we configure it to 1 on S and 0 on R, then we'll store a 1 here in the latch. If we do it the other way around, we're going to store a 0 in the latch. 0 is when gear is down, and 1 is when gear is up. So this is lift gear up. So when this is true, we want to make this be 1. So the appropriate thing to input here would be 1 and 0. When this is 1, we would want to input 0 and 1. And then when this is 1, we don't want that to happen at all. So we have to think of how to get that to happen, and I think we need some logic gates to make that work. So let's look at our logic gates real quick. And the one that comes to mind to me is the XOR gate, where the output is 1 if the inputs are the exact opposite of each other. And the reason I think of this gate, let's pull one down and think about it. If we connected up this guy, lift gear up, and this guy, input systems locked, into this guy here, the output of this is going to be a 1 when this is 1 and this is 0. And therefore, we'll set this to be a 1, and the gear is supposed to be, when the gear is up, right, it's supposed to be a 1. So that seems like that would work. What if we put another one here? So, when put gear down is 1, we want this to be a 1. We want a 1 to go in here and a 0 to go in here. And we want the contents of this to be a 0. So we need to get a 1 out of here. And again, if this is 1 and this is 1, we're going to be inputting a 0 over here. And if this is 1 and this is 0, we're going to be inputting a 1. So I think that this guy is going to do what we need it to do. And we'll go ahead and hook this up on camera quickly. Okay, so we need to hook that up to that, hook that up to that, and then we should ground that essentially. So let's do that. Let's grab a wire and connect that up. I think this is going to work. Let's try it out and see. Okay, first test worked. All the items are 0 and the output is 0. Second one, we have a 1 on lift gear up. The output should be a 1 that the gear is up, and that did work. Here we have put gear down is requested, but systems lock is requested, and gear up is still it's still in the gear up state, so that's fine. Put gear down is requested. Okay, and we go to 0, which is gear down. And this one, lift gear up, is requested, but systems are locked, so the output is 0. So that is correct as well. Good deal. Now we unlock some more stuff here, and we're going to memory. Right, so memory cell. Device memory is seen as part of microcontrollers or as detached memories of microprocessors, contain large numbers of memory cells. Each cell stores a word and an n-bit wide chunk of data, where n is typically power of 2 to make addressing more effective. which is also the smallest operational unit characteristic of a certain memory device. No smaller information than a word can be stored. I tell you, sometimes this verbiage here is a little much. I think it could probably be simplified. Our simplified memory cell will consist of in-bit wide input bus containing a number in-bit wide output bus to get the data out of the cell, and 3 signal lines: read, write, and select. These are the important ones for us to understand. Each cell has an address associated with it. An address decoder decodes the address coming in to the states of select signal lines. What happens with that is that when a memory cell is addressed and command to write in or read out data is issued, address decoder sets the select line to that specific memory cell to inform it about the operation that is to take place. We're going to be designing such a cell. Note, when select is 0, outputs of a memory cell shall not be assigned. Their state should be don't care or high impedance, which are the same here, in order to not interfere with a value possibly being retrieved from some other memory cell. I don't know that that's super applicable to what we're doing, but maybe I'm not fully understanding it. We're building a very simple memory cell here. Electronic circuit that stores 1 bit of binary information. It must be set to store a logic 1 and a reset to store a logic 0. Its value is maintained or stored until it is changed by the set reset process signalized by the write signal. The value in the memory cell can be accessed by reading it. Data in is a 4-bit data input. Well, that's the output. Data in, 4-bit data input. Read-write is a signal to determine the operation to be performed on the cell. It is taken into account only when select is 1. If RW is then 1, the cell's internally stored value is changed to data in. So our read-write is there. And our select is here. When it is 1, data out should be set to the internal state of the cell. It should not be assigned otherwise. Okay, I guess that's important. Alright. We might need a ground, we might need a high, I don't know. Grab them just so we don't have to navigate back here. I think we got all our bits. Let's see what we've got going on here though. Well, actually, we got more pages. Data out is dependent on the signal of select and the cell's internally stored value, and you will probably notice that the RW signal is somehow similar in meaning to the enable signal of some latches and flip-flops. Search for them in the components window. These are our multiplexers. Basic arithmetic. Here's our latches. So here's the SR latch, which doesn't quite do what we want it to do. But they've given us a new thing called the D latch, which is the first latch to at least distinctly resemble the nature of memories. D latch stores its internal state accessible through outputs Q and Q bar. Input E, or enable storage of the D data input so that D is stored only when E is 1. That sounds like exactly what we need. So, when E is 1, the output of D will be stored in here. This only is going to store 1 bit though, so we're going to need 4 of these. Hopefully I'm not putting them too close together to wire them up. So I'm thinking we wire D to each one of these guys, each of the D's on these guys, and we will wire write to the E, to the enable on each of these things, and then the output is Q, but we only want to be able to read Q when S is high, so we're going to have to do something else over here to make that work. And I'm not entirely sure what that might be. We might need these latches too to do that. So give me a second, a pause. I'll wire this up, and then we'll come back. Okay, guys, I think I got it here. I've taken the input of D, put it into the data side of this latch here, this D latch, and I've taken write and put it into the enable side. I've taken the Q bar, the output that we don't want, and put it into ground just so it's not hanging there. And now we have the output, but this output is only supposed to be sent to D when S is a 1. So how do we make that happen? My first thought was, well, maybe this SR latch But that's not going to work. So we only want it when this is a 1. And the value of Q could be 0 or 1. So we can't rely on what that's going to be. We don't know what that's going to be. So there's no way we can do it. So we need something to pass through only when this is a 1. So we need almost like a gate that's going to let through this data if this is a 1. And what is that gate? It's not SR latches, because SR latches, the inputs S and R define what its contents contain. Not S defines content and R decides whether it gets let through. Could we do it with another set of these memory cells? We could, probably. We would just make enable be S and pass this data from Q through to the new D, and then that would output it. But that's not going to work because we don't have any more of them. I mean, it would be a shortcut. It wouldn't be the right way to design a memory cell, maybe. It would be almost like, I guess, a buffer, I suppose, would be what that would be, where you're sort of buffering the memory. So let's go back to our other gates and see what we have. None of these gates are going to do it, because an AND gate relies on both inputs being a 1, but we don't know what one of our inputs is going to be. Same thing with an OR gate. It relies on them being, if either of them is a 1. So we'd be passing false positives up here because this is going to be a 1. I don't actually want the NOT gate. The NOT gate inverts the output, so that's not what we want it to be. And the only thing, what about a multiplexer? And the reason I think this is a 4-to-2 multiplexer, simplest multiplexer to input a pair of signals controlled by just a single select wire. This multiplexer selects either the first, select equals 0, or second, select equals 1 pair of inputs and moves it on to the outputs. 4-to-2. We would need 2 of them. So if we hooked select up to this guy, right, it would pass, when it was a 1, the second set of outputs, I believe it's going to be these, to these, and we could pass that through to there. These other ones we could just put, well, I guess we can't get these logical line lifters or lowers or whatever, so we'd have to just figure something out about that. I guess I could pull them low with a low input. Let's just take a low input. So we hook this up to these guys, to the first set, and then have this set go there. That may work. Let's try that. Let me wire it up. Okay, here we go. I got it wired up. I took away the low signal because it says that it's supposed to be undefined or do not care. Don't care or high impedance. High impedance. I don't know exactly what that means. I mean, that means high. Well, anyway, I don't know exactly what that means in terms of what its state should be digitally, so I can't really translate that. I don't think we should necessarily set it to anything, so let's just let it hang and see how that works. If it doesn't work, maybe we can stick a low on there and see. So we've inputted 0, 1, 0, 0, 1 on read write, a 0 in input select, and we get just random tripe on the output because it's just doing whatever it wants to do. Or is it passing through something here? Well, it let us pass. I'm not entirely sure that I've gotten these input sets right. It could be this half versus this half. In fact, it probably is, given that it has put this one through. Let's rewire these. Yes, it passed this one through as well. Okay, let's just take a quick break here. Let's stop the simulation. Take a quick break here and we'll rewire this, because I think we're not going to pass if we don't fix this. I wasn't sure how these things worked I don't know why I would have assumed it would go every other one. That doesn't really make much sense, does it? Okay, let's try again. This should still pass, hopefully. Yeah, now we have XXXX all the way across, implying that it doesn't even know what these things are. Let's go with number 2. We've got 8 steps here. So on this one, we got a data in signal, we got a read write signal, and we got a select signal, and it did in fact pass the value through. So that's good. Here we got 1, 0, 1, 0. We got a 0 in read write, but we got an input select, which passed. Was that the previous number? I think it might have been the previous number. So now we've actually passed the stored value of these through. We can double click to inspect this. 0, 0, 1, 0. Yeah, okay. So it passed through our number that we had stored previously, not the number that's currently on the data in. That's pretty cool. Okay, so we put in 1s. We have a 0 on the read write, so we're not even telling it to store that in the memory, and we have our input select at 0, so we're not telling it to pass through. So if we check this ought to be 0, 0, 1, 0 again. Yeah, it didn't store this 1, 1, 1, 1, 1 in the memory cell here. That's cool. Now we're getting to the interesting stuff. Okay. Now we're inputting all 1s. We're telling it to store that. We're telling it to select that and thus output all our 1s. And it's even giving us a handy hexadecimal F over here. This is the value of 16 that we're putting through. Or 15, I guess. Whatever. It's really 16. So, no, it is 15. Sorry, I'm being dopey. Let's see. We have 1, 0, 1, 1, a read, write, and a select, and we are outputting that. That's fine. We're putting in 0, and we have nothing on the thing, so we should still be storing the previous value, and we don't care what the output is, so that worked. And number 8, did it work? Yeah, we're putting in 1, 1, 0, 0, and we have, thank you. Let's return to the circuit. We have a 0 on the read write and a 1 on the input select, so we are not storing this data here, and we are passing through what is in memory out. So a 1, a 0, and a 1. So that worked fine. All right, well, that is it, and I think our next task is registers, which is left to an exercise for the readers. Unless you guys want to see more of this, and if you do, you got to comment. You got to let me know. And a lot of views on this. Don't think I've had any comments, but I had some likes and a couple of dislikes. I don't know why. So if you don't like it, that's cool too. There won't be any more of it. But if you do want to see more, let me know, and maybe we'll cover some more. We have quite a few more segments here to go. The game's a little borky, but I mean it's early access, so I'm not dogging it, and I'm going to keep playing it. So anyway, let me know if you guys want to see it, and if you do, leave a comment, please. I will talk to you soon. Thanks. Bye.